All right, so today we're going to be doing ideal gas law. So if you look in your notes, the next thing that shows up in the notes says something about Daltons. We're going to skip that for right now. Application of Daltons, and we're going to go to the back page where it says ideal gas law and its applications. And that's what we're going to be starting with or working on today. So that was our only quiz for this week. On Monday, y'all will have a quiz over what we did yesterday. So Avogadros and Daltons. And then this one, which is ideal gas, we'll have a quiz over that probably Wednesday of next week. I don't know that we'll finish this up to have a test before y'all go to spring break. All right, so if you look on your reference sheet, ideal gas law is what we're going to be looking at today. And it's different than what we've looked at because there's only one set of parameters. So like I don't have a P1 and a P2 or a V1 and a V2, just one set of parameters. We're also using something called R, which is the ideal gas constant in this formula. And the ideal gas constant is also on your reference sheet. Down here under your pressures. So here is your ideal gas law constant. And if you notice, it can have several different values. And what differs with each of these is what unit the pressure is in. So in other words, if my pressure was given to me in atmospheres, I would want to use 0.0821 as my R value. If my pressure was in kilopascals, I would want to use 8.31. And remember, millimeters of mercury and torr are the same. So if I had my pressure in either one of those, I would use my 62.4. This first one is the most common one. So if you're trying to find your pressure, then you would use that one. And then when you get your answer would be in atmospheres. All right, so let's look at our notes. All right, so this is our formula for ideal gas law. Like I said, it's a little bit different than what we have been doing. So P stands for pressure, V stands for volume, and it has to be in liters. If it's in milliliters, you're going to have to convert it. N is your number of moles. R is your gas constant. Is 0.0821 if your pressure is in atmosphere, or if you're trying to find your pressure. Then when you found your pressure, it would be in atmospheres. And R is on your reference sheet. And then T is your temperature, and it still has to be in Kelvin. As far as your pressure goes, depending on what your pressure is measured in, it can change your R. So I kind of showed you that on the reference sheet, and then we'll get to a problem where we can kind of see that difference. So the ideal gas law is derived from Boyle's and Charles's law, along with Avogadro's. And kind of we talked about this at the very beginning of the unit. There really is not such a thing as an ideal gas, but we assume that the real gases that we know behave ideally. That way they fit into all these different laws that we look at more easily, more mathematically easily. So it gives us a close approximation. Real gases behave most like an ideal gas at high temperatures, low pressure, and when they're non-polar. And that's anything that allows them to spread out and not have any attraction to a gas particle next to it. That's what's going to, when a real gas is going to behave most like an ideal. So at high temperatures, a lot of energy, they're moving around, low pressures, allowing them to increase their volume. And if something is nonpolar, it would not be attracted to each other. So all of those things help gases to behave more like ideal gases. R is the ideal gas constant, and it has different values. And then our temperature still has to be in Kelvin also, like we've talked about before. So right here, these numbers right here are just showing how the ideal gas constant is derived. So like I said, this is the most common one, your 0.0821. So if pressure is your unknown, if that's what you're trying to find, you would use this, and pressure units would be in atmospheres. And we'll look at an example of that. So you can do one of two things as far as your R goes. Any kind of pressure, you can change it to atmospheres and then always use 0.0821, or you can change out your R values based on the pressure that you know. And that's kind of what I like to do. I think that's a little bit less work. And like I said, we'll look at a couple of those here shortly. All right, so let's look at some of these. And I'm just going to jot down my formula. PV equals nRT. So it says what pressure will be exerted by 0.4 moles of gas. So there's my N. My pressure is going to be my unknown. In a 10-liter vessel. So there's my volume, and it's already in liters, so I don't have to convert it. And then my temperature, I'm going to go ahead and add 273 to it. And that would get me to 300 K. All right, so now I have everything I need. So I'm just going to start filling in. So P is my pressure. That's my unknown. B is my volume in liters. So that's my 10 liters. That's going to be equal to my N, which is my 0.400 moles. We said if pressure is unknown, we use our most common one as far as our R goes. So that's 0.0821 atmospheres. Atmospheres times liters divided by mole times Kelvin. And then my temperature, when I changed it, I had 300 K. So there is my setup. At this point, as far as units goes, Kelvin is able to cancel out and moles is able to cancel out. So I need to get my pressure by itself. So I'm going to divide each side by 10 liters. That allows my liters to cancel out. I'm left with just atmospheres, which I should be since I'm trying to find pressure. So this is what needs to go in your calculator. So if you'll put that in your calculator and see what you get. And how many sig figs would we have? 3, exactly. End up with 3 sig figs. All right, so what did we get for our pressure? Perfect, 0.985, and ATM would be my units. All right, anybody have any questions on that one? All right, let's look at one more here, and then we'll kind of change up our scenario a little bit. It says, I have a sample of methane gas, and it contains 1,500 liters, at a pressure of 15 atmospheres and a temperature of 45 K, so that becomes 318 Kelvin. How many grams of methane are in the sample? So if I think of my ideal gas law, let's see what we have at this point. I have pressure, that's my atmosphere measurement. I have volume, that's my liter measurement. I can always have R because that's just a constant, and I have T. So the only thing I don't have is moles. So I can solve for moles. Once I know my moles of methane gas, can I get to my grams of methane gas? Right, just by using the molar mass. So that's what we have to do. We have to solve for our moles, and then we'll use our molar mass to get to grams. So I'm going to start plugging everything in. My pressure is 15 atmospheres. My volume is 1,500 liters. N is what I'm trying to find. My pressure is in atmosphere, so that means I'm going to use my 0.0821. And then my temperature in Kelvin was 318. All righty, so I need to get my N by itself. So I'm going to multiply by 0.0821 times 318. So how many sig figs are we going to have? 3, exactly. Remember, R is a constant. It wouldn't affect your sig figs. All right, so how many moles did we get? 862, perfect. Moles of methane, but we wanted grams of methane, so we're going to use the molar mass. So that says 1 mole of methane has a mass of 16.05 grams. That's what I get from adding the mass of 4 hydrogen and 1 oxygen. So my moles cancel and I multiply across, and I still need 3 sig figs, and that would tell me how many grams. Perfect. 13,800 grams. Think you got something like this from the calculation? But we said we could only have 3 sig figs, so that's where my 8 is. So there's a 3 behind it. I don't raise it up, but I do need to put placeholders. So that's where we would get our 13,800. All right, any questions on that particular one? In AP chemistry, in college chemistry, they love to use the ideal gas law because you can get a lot of different things from it. All right, let's look at one where we have a different R value than what we've been using. You good? All right. All right. We'll just skip through that first one because it's still an atmosphere. So let's look at the next one. All right. So it says find the volume of gas. So right away, that tells me that's my unknown. At 103.7 kilopascals, 37 degrees Celsius, which would become 310 K and 1.7 moles. So this time my pressure is in kilopascals. So look on your reference sheet, and which R would you use instead of 0.0821? 8.31. If you look at your reference sheet where you see that R 8.31 behind it has the kilopascals. So that's what we would use on this one for my R value. So The other one had atmospheres. This one has kilopascals. When you change your R out, this is the only thing that changes is the pressure. All right, so now we can just start filling everything in. So pressure would be my 103.7 kilopascals. My volume is my unknown. My moles, 1.7 mole. We said we're going to use 8.31 as my R value, and my temperature is 310 K. All right, there is my setup. I need this V by itself, so I need to divide each side by 103.7, 103.7. That cancels, and then this is what should go in your calculator. And because of that 1.7, my answer will only have 2 sig figs. Everybody able to get 42 from it? All right. So do y'all understand how you would change out your R value? All right. Why don't y'all try this one? It should not be 10.6. Your answer you should get is 11 K, because you only can have 2 sig figs. So a couple of things you got to do here. One thing is, if you notice, your volume is in milliliters, so I need to change that to liters. So how many liters would that become? The 0 you wouldn't count, because here the 0 is not significant, so I don't want it to be significant when I convert either. So 0.35 liters, just having 2 sig figs. And then the other thing that you have is you don't have how many moles of oxygen gas, you have how many grams. So you've got to convert that to moles first by using the molar mass. And don't forget, oxygen is a diatomic. So this one's got a few more things to it. So see if you can get that one. No, you don't. You can leave it as Tor and then just pick your R. Because remember, one R says millimeters of mercury, and the millimeters of mercury and Tor are the same. So just, and you might want to write that on your little sheet. So just where it says, your number will be the same, and then where it says millimeters of mercury, you'll just put Tor in there. So 12.5 grams, how many moles of oxygen did that give you? 0.391. And if you did it as 0.39, it may not have changed your answer. Well, but so your final answer, you're right, will only have 2 sig figs. But when you're doing, I can't even think what I'm trying to write here. When you're doing this one particular calculation, okay, and then what is it, of 32 grams per 1 mole. In this particular calculation, you're using 3 sig figs. See, you're not using that 0.35. So that's why your answer would have 3 sig figs at that point. But that's a good question. So that's why you would have, and like I said, it may, did you still get 11? Yeah, so it may not have changed your answer. All right. So was everybody able to get 11? Yes. Do I need to work through it? Yes. Okay. So P is my 737 torr. My volume was my 0.35 liters. N is what I had because I can't put grams in. So we kind of looked at one of those yesterday. Since it is in torr, which is the same thing as millimeters of mercury, then I picked my 62.4. And then I'm actually trying to find my temperature, right? All right. So did you get that set up, Caleb, at that point?
I forgot that you.
Okay. And that's, yeah, and that's a little tricky one because that messes you up. So, but it has to be in liters. So now at this point, I divide by 0.391 times 62.4. And same thing over here. And now at this one, it has to go down to my 3 sig figs because of my 0.35. So when you did that, you would have gotten 11K. And then to get it in Celsius, you would subtract your 273. And that's why you end up with your negative 262 degrees Celsius. All right. Any other questions on this one? Adrian, how are you okay on it? Okay. So there's a couple more on there that you can try that we haven't done yet. See if you can get those answers. I think probably this one right here had the most little weird things that you kind of had to do extra. So try those 2 that are on here. I think you have enough time to do those next week, next Wednesday. So that'll give you time to do some practice and have time to ask questions if you need to before we quiz. I don't know yet. I need to look over it. Okay. I don't know that we will get through it because we have the gas stoichiometry that is kind of hard. So
is it going to be on with this, like this?
For the quiz?
No, for the big test.
Yeah, the big test has that up there. I'm not going to quiz separately over the gas stoichiometry. We'll just do it on the test. So I need to look over my notes. I may be able to give you a better answer tomorrow. Okay, so you're gone Thursday, so you know what you need to do. Okay, and you're gone. So, and you know what you need to do Thursday, and I'm gonna try to have this to you by the end of the day. 8th period, Mrs. Brown. Okay.
Is there a worksheet too, or just?
I'm just gonna do it. It's easy for the sub and easy for me.